Hi, and welcome to this short lecture about the mole, a chemist's way of counting atoms and molecules. From this lecture, we hope to learn about the mole and how it relates to counting atoms and molecules, and also, and probably more importantly, to be able to convert between the mass of a substance and the number of moles and atoms present in that mass. After this lecture, don't forget about the short Canvas quiz to be completed. This lecture ties in with our major themes of the course of scientific measurement and understanding and their uncertainty in the world around us. So first, a little bit of information about the mole. Atoms and molecules are really small. You know this, and that's an understatement. But what we're going to try and do is put this into a little bit of perspective. It's hard for chemists to talk about what happens with a single atom or a single molecule. And most of the time, instead, we talk about what happens with a collection of atoms or a collection of molecules. And so the mole is really a way of counting these collections. We do this all the time in our regular life. For example, we often talk about a dozen eggs, and this refers to as 12 eggs. We also use words like century, score, and the mole is just the chemist's way of expressing the same thing. Each mole has a given quantity of atoms, a given quantity of molecules present. So we will talk about counting by moles of a substance. The concept of a mole was developed by Avogadro, shown here, and immortalized in an Italian postal stamp here. And Avogadro's number, which has been abbreviated capital N with a subscript capital A, is defined as the number of atoms in 12 grams of carbon-12. And that has been determined to be 6.022 times 10 to the 23rd. So a mole, and chemists abbreviate mole as MOL. We drop the E because we're lazy. The mole is defined as the amount of a substance that contains 6.022 times 10 to the 23rd particles. So a mole can be anything. It's a mole of things. And this word particles, we might have a mole of atoms, a mole of molecules, a mole of cats. It really doesn't matter. It's just this number of things in that group. If we had 2 moles, then we would have twice the number of atoms or twice the number of things in that group. So just how big is 1 mole? And another way of looking at that is just how small is 1 atom or how small is a molecule. This is a really big number, and to try and put it into a sense of perspective, we can think about there's 7 billion people roughly living on this planet. And so if we were to write that number, here's what it would look like. We know if we counted 1 grain of sand every second for 80 years, so if you just sat there and counted grains of sand every single second for 80 years straight, you would count to 2.5 times 10 to the 9th grains of sand. And if we write out that number, here it is shown. Now, if all 7 billion people on the planet counted grains of sand for 80 years, so 7 billion people counting grains of sand for 80 years, collectively, we could count to 1.5 times 10 to the 19th grains of sand. This is a lot of sand, shown here. But notice, this is 10 to the 19th. This is still 4 orders of magnitude smaller than 1 mole. This is still less than 1 mole. If we were to write out 1 mole, it would look like this. Right? That 1 mole, 6.022 times 10 to the 23rd, is an enormous number. And all of that can be contained in a small amount. So here's 1 mole of carbon, 12 grams of carbon, shown here. And we have 6.022 times 10 to the 23rd atoms making that up. Avogadro's number in the mole gives us a way to convert between the number of moles and the number of particles. And we need to be good with these conversions. So, for example, if we were given a problem where we said we have a glass of water that contains 28 moles, and we were asked how many molecules of water are present. So if we're going to solve this problem, we're going to start with the number that's given. So we're given 28 moles. So start with the 28 moles. And we're going to multiply by a conversion factor. And that conversion factor is Avogadro's number. Now notice how I set this up. We want to end up with the units of molecules. And so we're starting with moles, So we want moles to cross off, so I set it up so I'm multiplying by Avogadro's number. So moles is on the bottom, crosses out my starting moles, and we end up with 1.7 times 10 to the 25th water molecules. When we get to the answer, always ask yourself, does this make sense? And hopefully it does. We started with more than 1 mole of water, and so we ended up with an answer that's bigger than Avogadro's number. We can do the reverse process, and we can imagine a problem that said the tip of a pencil with a mass of 15 milligrams contains 7.5 times 10 to the 20th carbon atoms. How many moles of carbon atoms are present? So we're going to solve this in the same fashion. We're going to start with the number that's given, 7.5 times 10 to the 20th. And now we're going to use Avogadro's number as our conversion factor. But notice we want atoms to cross off, so I'm going to want atoms on the bottom. So now I'm going to divide by Avogadro's number. So 1 mole over 6.022 times 10 to the 23rd. That way my atoms get crossed off, and we're left with 0.0012 moles. Again, does this make sense? We started with less than 1 mole, and our answer is less than 1 mole. So by definition, if we go back to this definition, a mole is defined as the number of atoms in exactly 12 grams of carbon-12. And this has been determined to be 6.022 times 10 to the 23rd. Now, we can then look at the periodic table, and one of the things I want to point out in the periodic table, here I've taken out the elemental symbol from carbon on a periodic table. Notice the atomic number 6 protons, atomic symbol capital C for carbon, and then notice we have a mass here. This mass is the mass of 1 mole of that element. And the units of this are in grams per mole. So the periodic table gives us the molar mass of every element on the table. But what I want to draw your attention to is this is not 12.00 as by definition in our definition of the mole. So why is that? Why is the element carbon not have a molar mass of 12.00? And the reason for that really comes down to this last part of the phrase, 12 grams of carbon-12. And so when we think about carbon as it exists in nature, carbon can exist as a number of different isotopes. Remember, an isotope, atoms with the same atomic number but different mass number. So carbon can exist with 6 protons and 6 neutrons, that's carbon-12, 6 protons, 7 neutrons, that's carbon-13, or 6 protons and 8 neutrons, and that's carbon-14. And when we think about what is naturally abundant, what is around in nature, we see that in nature, 99% of all the carbon is in fact carbon-12. 1% is carbon-13. And then a very, very small amount is carbon-14. And so when we think about this, the mass that's on the periodic table is really a weighted average of these three, taking into account their natural abundance and their mass. So if you look at the periodic table, and in this case, all of the masses in red shown on the periodic table, each of these represent the mass of 1 mole of the element as it exists naturally, taking into account the fact that there are multiple isotopes of many of these elements present. Okay. The other thing that this gives us is a relationship between the mass of an element and the number of moles present. So, for instance, we can look at a problem where if we have 1.22 times 10 to the 23rd atoms of helium, how many moles are present? And also, what is the mass of that helium? How many grams of helium do we have? So when we go to answer this question, we're going to start off the same way as we did before. We're going to start off with the number that we were given first, and we're going to convert from atoms to moles. So we're given 1.22 times 10 to the 23rd atoms. We're now going to divide by Avogadro's number. Again, so our atoms cross off, and we're left with moles. So in this case, we have 0.203 moles, and that's moles of helium. Now what we need to do is convert that into mass. So we're going to start with the 0.203 moles. Right? So here's our 0.203 moles. And now we're going to go to the periodic table and we're going to look up the molar mass of helium. So we can see from the periodic table, 1 mole of helium has a mass of 4.00 grams. This is the molar mass of helium directly from the periodic table. And notice how I set this up. We want to end up with grams, so I put the grams on top. We want the moles to cross out, so I put the moles on the bottom, so they cross out with our starting moles. And we end up with 0.813 grams. Again, ask yourself, does it make sense? Well, we started with less than 1 mole of atoms, right? And therefore, our mass should be less than that of the molar mass of that element. And in fact, that's what we have. So what's shown on this slide here are the ways we can convert. We now have a way of converting from the number of atoms of something to the number of moles. And anytime we're going to go from atoms or molecules to moles, we always want to use Avogadro's number. If we have the number of moles of a substance and we want to go to mass, the way we're going to do that is always using the molar mass. The only thing we have to watch out for is, are we multiplying or are we dividing? And that's where you have to watch your units to make sure they cross out appropriately. So that ends this lecture. So still to come, we have to learn how to deal with molecules and their molar masses in these conversions. And these types of problems, they'll be with us for the rest of the semester, as long as you stay with chemistry. So it's really important we become very good at this calculation and these conversions. Don't forget to complete the short Canvas quiz. Thank you for watching.